I think the program assignment has been too big without chopping them to smaller chunks, and students don't start early enough and making them too difficult. So this is a homework designed to be part of the program assignment too. Okay, so I'll walk through this when we in the content that we can walk through. Okay, we can walk through this. So today, I'm going to talk about a Wilkinson principle. Okay, and we'll use the linear algebra as the sparse matrix as an example how this can be applied in two ways. Okay, I'll tell you what is Wilkinson principle. You probably know the principle, you just don't know it's called Wilkinson. Okay, it's something that's rather commonly done for verification. Okay, commonly done for verification. Okay. Okay. So from the last hacker practice, you should have remind you about all the tracing of the index of how do you access data, and when you have something wrong in indexing or the pointer is wrong, you get the totally wrong results. Okay, and that still happens. Okay, especially when the data structure become more complicated, or when there are some operations that actually operate directly on the pointers for efficiency. Okay, for efficiency, and those are quite common. Okay, and when those are wrong, they're very difficult to check. Okay, very difficult to check. So it is a good thing that you do validations through two different data structures to check your indexing or thing scheme. Okay, just carefully walk through the known examples of different indexing method is not sufficient usually for identifying the indexing errors or indexing bugs. Okay, but if you do two different data structures, which I'm going to show you, very soon how it can be done. Okay, and this is basically your homework I just passed down. Okay, and we can have a better modular testing. Okay, for every operations, you can write these modular testings using these different data structures to implement the same thing. Okay, sometimes it's not the different data structures. Sometimes there are the different computational routes, different approximations. Okay, different something, but it's two different things to arrive at the same answer or the same computable answer. Okay, to computable answer. Okay. So intuitively, this is something that you should say, oh, this is the well check, right? If you have two independent implementations, and if they give exactly the same answer, then the probability that both implementations are correct is very high. Okay? And this also assumes that you don't need to know the ground truth, right? You're comparing two approaches. Neither one you know the ground truth, but since if they're incorrect implementations, if the answer you eventually get is the same, then the probability that both implementation is right is very high. Okay, this is formulated. Okay, called the Wilkinson principle. Okay, what is that? Okay, let me tell you what it is. This actually can be applied to many situations. Okay, many situations. Let me. What is exactly Wilkinson principle is this? Okay, a computed solution. Okay, X is the exact solution of a nearby problem. Okay, even your computed X has errors, has bugs, but it is the exact solution of whatever you specify, or exact solution of a perturbed problem, right? So maybe the parameter you give is not have sufficient precision or things, but this is what you computed is the exact solution of what you give. Sure, right? This is so this is for sure. Why is this a principle? Okay, but this is important, right? In many ways. So if you have, right, if I paraphrase with the data structure, okay, the computed solution X with incorrect implementation is still an exact solution of your wrongly specified problem. If you implement it in two data structures, the chances that they are exactly wrong at the same place are very, very small, right? So if you check a answer, a computable answer, okay, instead of symbolic, okay, you check a computable answer, but you use two data structure to compute the same thing, okay? And if the number appears to be the same, then the probability of both are correct is very high. Not for sure, okay? If you have the same error, same algorithm error in both implementations, then this is not right, okay? So the check, the validation is useful, but we know it's incomplete, right? In physics, this is like, okay, that if I do average, right? If I do average, I can remove the random noise. For sure, if you have the same wrong systematic bias, then there's nothing you can do about it by this method. But what is randomly wrong can be checked by this, right? Your coding errors, most of the time, is a random error, okay? Suppose you should implement divided by 2h. But what you implement, you put down is divided by 2 times h. It's a random error. If you do another route of that implementation, chances are it won't happen at the same time, at the same place, right? So if the two implementation give you a computation exactly the same answer, then likely from this principle, right, the probability that the both implementation are right is very high. You check something, okay? You have check something. So this is possible, okay? So let's do this in a software validations with this is very useful, okay, in the software validation method, okay? And this is actually a 101 rule in accounting, okay? If you have friends doing accounting, you will know that every day, that at the end, the close of business day, how do they verify their results? How do you know that the cashier hasn't entered something wrong and the bank is going to bankrupt tomorrow? How do you know that? So in accounting, right, 101 principle is always two route, okay? Always two cashier and doing almost the same thing. And they check the result, are they consistent? As a first defense, it's usually not sufficient, okay? It's incomplete, but it's very useful check. Will read off many of the random bugs. Okay, in accounting, this is a 101 principle. There are other more evolved theory. Okay, that's what accounting can do to check the results. But the Wilkinson principle, it's one that's constantly be invoked. You do two, even usually the accounting, the computation is so easy. Okay, you just sum, average, compound rate, or all these things. But they do two implementation, two cashier. If they check the results, if the results match, chances are, okay, match to the last digit, chances are it will be correct. Okay. So it actually can be more famously used when you have two algorithms. Okay, when you compare the results of the two algorithms, you can also know how much error I'm dealing with, right? That's for sure assuming that two algorithm has no implementation bug. Okay, so when you know there's no implementation bug, this principle can be further used, right, to check. Okay, now they don't give exactly the same answer. Okay, so I can roughly estimate what kind of error I'm talking about. Okay, that's also part of the Wilkinson principle. Okay, so it's just that when you use two or several different approaches to get a computable result, okay, this is one of the easiest way to automate your verification, right? So this is very different from your checking your code, what is wrong, right? That's symbolic, that only human can do it. This is something easily automated, right? Because you're checking the consistency of two computed results, right? Okay. So let me give you a solid example, okay? So for matrix operations, okay, these are the three very basic operations that happen every day. Okay, you can do this in. I'll show you how to do this in actually only matrix computation that leads to something called LU decomposition. Okay, but that will come. Okay, but let's just at this end at now, let's have three matrix operations. Okay. Row permute, okay, you permute the order of a row, okay. So for sure, that shouldn't change the property of the matrix. If you permute AX equal to B, permute your B together with A, then it shouldn't change the solution at all, right? Can't, right? You just change the order of your row representation. That shouldn't change the solution or the property of the matrix. For sure, permuting your rows or columns has a very deep mathematical meaning in it, okay? Because which row you deal with first is related to what we're going to teach you, what is pivoting, okay? When you think about, when I deal with my matrix, the diagonal is very important. What is diagonal, okay? Diagonal, actually, if you change the permutation, diagonal element changed, right? If you think about your matrix, okay? Oh wait, I need this. I'm sorry. If you have your matrix like this, right? So this is your diagonal, right? If I change these two rows, right, the diagonal element changed. Okay, it shouldn't change anything, but it changed what you think is more important when you use that to operate on other rows. Okay, so permute is loop dump. Okay, it's actually very important in computation. Okay, I'll show you. Okay, row scaling means a linear algebra operation. I times get a row, okay, scale it with a double A, and add it to another row. Okay, you scale row J by row I. Okay, that again, if you do that together with your B, it shouldn't change the solution at all. It's the same solution. Right. So just it's called row scaling. That means that your the row factors of the matrix, right, a scale to another row should not change the matrix solution at all. Okay, but it's a very essential operation of the matrix. The last one is vector product, right? Calculate what is A times X. Okay. Just with these three, actually, you can already implement matrix solutions. Okay. Just these three operations, okay, is good enough to get a diagonalizations or LU decomposition. Is basically these three steps, okay. So, okay, so assume that I have these three steps I need to implement, okay. And if I implement it, right, for my, okay, this is usually implemented with all these matrix pointer, vector pointers, okay, return an integer. The integer usually where you have learned to control your exceptions, okay. So if exception has been met, you use that to return the value, okay. Remember, exception shouldn't halt your computation because that price is too high, okay. So you use that integer to return whatever the exception you think that you need to handle. Okay, so these are something related to a previous exercise. Okay, and if you want to improve the readability, instead of returning 0 and 1, define some macros for your global variables for that return value. Okay, so it's more readable. Okay, that's okay. Okay, easy things. Okay, but if you implement the three method in both full matrix and your sparse matrix, okay. Implement twice, okay, and then you can check after initiate some random sequence of those solutions, okay, you should get exactly the same matrix, right? Have to, right? It's just different data representation, okay. You can check row by row, okay. You do not need to know the ground truths. There's no ground truths here, okay. Just that, but you just implement the three matrix operation in two data structures. Okay, input choose a random matrix, and then compare your full matrix answer, sparse matrix answer. Right? Have to be identical, element by element. And then you know, okay, my sparse matrix indexing schemes and algorithm are most likely correct. Right? By this very simple check, right? Okay, so that if you have software bugs, right, it's likely you can find it, okay, in a simple test. Okay, your simple test will fail if you have a software bug in these three methods. Okay, for the sake of time, let's implement one. Okay, let's implement the last one, which is the easiest. Okay, the previous two, these two are not so easy actually. Okay, because it changed the sparse structure. Right, you permute the rows. Right, the row index change is actually a pretty complicated in your sparse matrix representation. Right, you do row scaling, they will have fill-ins. Right. Originally, this is a 0. If you times a constant to add to another row, you may change the sparse structure. Okay, so these two looks easy, it's not so easy. Okay, in your data structure. Okay, so that's exactly in your homework. Okay, so your homework you are going to implement all these three. Okay, and do that. But let's in the class let's at least do a you have from the last practice. You have that sparse matrix in the row index, row pointer, column index, and the value of this matrix. Let's do a times x. Okay, let's do a times x, and you have a b, right, generated. Check element by any of the full matrix representation, which probably most of your things have a built-in function, or it's so easy to write in the full matrix, so easy to write, right? A times x. Compare your b. Okay, compare your b, item by item. Okay, and when you compare, it's usually easy, right? You want one report, right? You want to do one report, so you will do that b generated, right? B generated I by your sparse, right? Minus the bi. That's your full matrix. You do a second norm, right? You compute this number, right? This number should be very close to 0. If it's not close to 0, you report that there's something wrong, right? Let's implement this, okay? From your last sparse row compressed storage method that you have done in class, okay? Do ax equal b, okay? And do the ax equal b in your full matrix, okay? Which is so straightforward, okay? And then compute this, okay? Try it. Even if you cannot finish, I want you to give a serious try, okay? So that this will be, when you do your homework, it's much easier to you at least know what is clear, not clear. You can do your homework much easier. that's what you have last time, right? That matrix in the compressed row format. And from this, right, how you transverse your matrix element to perform an A times X, okay, should be something that's, if you have that representation, should be doable, okay? Anyone has that? If you didn't finish the retrieve element then last time, then probably you cannot finish in time then. Any questioning how to do this?
First, do we have to multiply using this?
Right. If you have this retrieve element function, it's just 2 for loops, right? The first is going through, select the retrieve the row, first row of the matrix, times with the correct column index with this vector. Sum it up, right? Walk through the column. You get the
just
B.
calculate the product.
Yes.
Just the product.
Yes. And then use the this matrix in full matrix, load the full matrix as Aij, full matrix representations. Then that's even easier, right? So accessing the add method is just Aij, right? And compute A times X, right? And the two implementation should give you identical B elements, right? And then you get the second norm of the B factors. The B factors should be identical. Okay. If you didn't aren't able to finish, it's probably you didn't finish the retrieve element last time. Okay, that's okay. Okay. But this is the show you how a modular programming should be, right? So if I ask you to do a function of A times X, product AX, then if you have the retrieve element, it's much easier to write, right? And the retrieve element or retrieve element in sparse matrix and retrieve element in simple full matrix, then it's the same 2 for loops to compute to do the product, right? Product AX. Okay, I won't use the lecture time to wait for you, okay? So if you take a copy of the homework, okay, let me tell you that what I expect you to do within a week, though. This is short, okay? But I want you to finish. so that we can start a much more meaningful program assignment too. Okay. So basically, the first part is just what I described. Okay. The computation is a little bit more complicated. Okay. But not much more complicated. You permute some rows, do some scaling, okay, and then do the x equal to b, okay, in sparse format, in full matrix format. In full matrix format, okay, it should be like 5 minutes in your 2110 assignment, okay, trivial, okay. So, but now you do the sparse format, right? Using that to check whether your sparse format in that method are correct. Okay, first part, okay. Start that immediately, okay, that should be finished very soon, okay. The second part will spend a little bit more time, okay, and that's real, okay. So what I'll give you is already on the blackboard, a pretty large matrix, okay, of rank about 20,000, okay, and this is actually a very small memory circuit, okay. It's one row of your DRAM memory, okay. So from that, okay, the matrix is sparse, have the sparse structures I show you, okay. So this one you cannot, okay, if you can try to declare full matrix of 20,000 by 20,000, okay, most compilers should kick you out, okay, because it doesn't have that much memory. So you have to deal with in the sparse matrix, okay. So that also means I cannot use the same method, the full matrix and the sparse matrix to perform the check, okay. But remember, I have checked my routine sparse matrix format already with a simpler example. Okay, so both part 1 and part 2 are required, right? When a smaller scope of check can be done with different data structures. A larger scope is going to be done by checksum. Okay, I use 2 different ways to arrive at the sum of all elements. Okay, one through these permutations, and then times a O1 on the x. Okay, x is O1. Okay, so that can calculate a sum of all non-zero elements. And you're going to just walk through all the non-zero elements without dealing with the index and arrive at a sum. Okay, compare that to checksum. Okay, 2 different ways of computation on the same data structures and see whether you have done it correctly. Okay, but this is a more realistic sparse matrix. Okay, you cannot use a full matrix to check. But remember, you have check on a simpler example on the full matrix. Okay, so don't do this part 2 directly. Okay, check your routine is correct against the full matrix on a smaller matrix before you try the gigantic matrix. Okay, much easier to do. Hopefully you will see some bugs and the checksum is not correct the first time, not consistent the first time. Okay, then with the part 1 check, much easier to debug. Okay, hopefully that this assignment purpose is that you can show when you're dealing with large data set, how the debugging process. Okay, debugging process. It is reasonably clear. Part 1, part 2. Part 1 using a known small matrix, use two different data structures to verify that you have done your sparse matrix method correctly. Second check, I can only have sparse matrix. Okay, I do 2 checksum. Okay, and this, if the answer is consistent, you hope, you believe, right? This is your implementation is correct. Yes.
The 2 data structures that we have to use, they'll be row compressed and column compressed, right? Or
I only ask you to do row compress. Okay, checking row compress and column compress many times is less meaningful. Okay, you can still do that. Okay, but if I have a column compressed format, I will check first with my full matrix first. Okay, because it's more solid check. These actually check with a full matrix, all elements, it's a fuller check than the checksum. but it's not possible to do on the big matrix.
Right.
Right? So I show you two things. Okay. So in the assignment, I ask you to do the checksum, not to re-implement a compressed column. Okay. You only need to implement a compressed row. Okay. Is the homework clear? Only 1 week, so please start early. Okay. If you know what I want, it's not a hard assignment. Okay. But please start. Okay. Please start. Yes. Can I what?
I have a doubt, like this row pointer indication.
Yes.
So zero says the first row start, the zeroth row starts with 0 elements.
Yeah.
So the 3 says after 3 elements the first row starts.
Second row start. The order cut. Yeah. Okay.
0, 1.
Yeah.
So the 6 represents after 6 elements the third row starts.
Yes.
9 is after 9 elements.
Yeah.
So but the last element says 12. So should it, because there is no 6th row here. So
Yeah.
how do we?
But this one tell you how many non-zero elements you have, total non-zero elements, right?
Okay.
It's a convenience thing to have. Right. The last row pointers tell you the total non-zero elements. Okay. But first implement retrieve element. Okay. Retrieve using that. Okay. Don't jump through assignment. Okay. The assignment is done through the hacker practice and things are step by step how I will write it. Okay. Okay. And you can. If you directly write, okay, imagining you try to jump over all these things, and the assignment is just put this part 2. And something is wrong. The debugging is much harder. Okay, and that's the purpose of this assignment is step by step, right? Introduce you this and also show you how when you do your modular programming, what is the task that's possible to go along with each module. Okay, the example probably is too simple that this is a overkill. Okay, but it's a example I want to show you. Okay, modular programming go with their own test, and gradually making more and more complex tests that's not possible to run simple test cases. Okay, and the procedure I show you here is simple, okay, but it's very good illustration of what you should do for dealing with large problem, right? Write smaller modules, verify it, write simpler method, verify it before you attack the large test that you can do some only limited validation. Okay. If the only thing you do in your future job is linear algebra, then this is one beautiful example, okay? But for sure, your job will involve much more complicated problem, okay? But the thought process is the same, okay? The software engineering part is the same, okay? In the Wilkinson Principle, right? Write something you can verify, okay? 2 different methods, okay? In smaller data structure you can handle, okay? Verify your method, okay? 2 different computation methods when only one data structure is possible. Okay, different tasks cover different domain. Okay. Okay. Any questions? Okay, now you are all here. And my travel schedule also settled. So I will be away in DC again for these 2 days. Okay. Next Monday is a February break. Okay. So we don't have class on next Monday or Tuesday. Okay. That's regular. Okay. But I have to be away for a Monday and the Tuesday and the Wednesday for this week. Okay. I will be in DC for a meeting. Cannot get out of it. Okay. So I propose that we have either a makeup in this day or this day, makeup lectures, okay? So this one is actually right after your February break, next week, next Thursday, and this is the Thursday next. Which one do you prefer? What? March? March? Anybody prefer this? What? February. Okay, one vote here. And March has, let me show you hands. Only 1, 2, 3, 4. Okay, 1, 2, 3, 4. And this one, February, also 4. Okay. Yes.
Can I ask you about the specific time of the
7:30. It has to be at night. I mean, this daytime is not possible for most people. So 4 to 4. Oh, okay. What?
We have 9 people.
Yeah. Who is the tiebreaker? Let me do it again. Okay. This date. Show hands. 1, 2, 3, 4. Okay. You raise 5. Okay. And for sure, this is 4, right? March date. 4. Okay. So let's do it this one. Okay. Next Thursday, I'll send out announcement about the room and things. Let me makeup class. You don't have to eat dinner. I'll prepare pizza. Okay. So it's coming with empty stomach. We can have.
Anchovy.
What?
Please don't do anchovy pizza.
Don't
Anchovy pizza.
anchovy.
Don't do that.
Don't do that. Okay. 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 I won't have anchovy. Okay. If you actually have preference, for sure, I will order something vegetarian and something non-vegetarian. Okay. But anchovies is crossed out. I'll remember that. Okay. Okay. So I'll send further announcement for where the location and things. Okay. Okay. It's better that this right before our homework due. This homework. Okay. Okay. Let me finish today. Okay. With I probably cannot finish the part at I want to do the matrix types. Okay. But I can finish this. Okay. There are other types of Wilkinson validations. Okay. So this is to explain to you about the homework. Okay. You check the norm of ax ax minus b. No, sorry. We check. This is the second homework. Okay, that you can do different computational procedures to arrive at a checksum. Okay, there are different methods. In addition to data structure, you can do. Okay. And there are examples where Wilkinson principles is used to check two different algorithms or two different conditioning methods. Okay. And sometimes you want to check whether your quad precision is done correctly. And simultaneously, you want to check whether a specific answer is wrong because of the conditioning of the matrix. So you do double precision or single precision, double precision. Compare these two, okay? You can check the conditioning, right? Same algorithm, but just the computation is made, one in single precision, the other in double precision, okay? And if the answer is correct, okay, the same, that means, okay, my computation my matrix is well conditioned, okay? But it's wrong, then you probably have to check. It's so different, you have to check double and quad. Okay, something like that. Okay, a different thing. Okay, and think about your test. Okay, many times some tests are meaningless. Okay, so if you check ax minus b for product ax, it's not a check. The only thing you check is the norm, right? If you check ax minus b for given b and solution of x, then this is a very meaningful check. But this is not a meaningful check at all if you just check the ax, because it's the same matrix you get, right? Same vector you get. You didn't check anything, okay? If you check ax minus b for that product ax, okay? The only thing you check is the norm. So that it's not that the more tests you have, the better. When you write down a test, think about what these tests cover. Okay, what did it check? Okay, that will take training in the long term for you to do what is the task space that I cover? Okay, on the digital computations. Okay, that is actually a formulatable way of proving what task have covered what kind of percentage of your system. Okay, it belongs to a class called testability of digital systems. Okay, for analog system, that theory doesn't exist. Okay, you cannot evaluate for an analog system to cover the testability. Okay, that only exists in digital world. Okay, so but it's still helpful. Okay, for you to have going to a class of testability. Okay, they will tell you how you can calculate the testability using different test vectors for a system, digital system you're dealing with. Okay, the real world, unfortunately, that doesn't exist. Okay, because you can see probably testability is always built on a finite space, and digital space is finite. Analog world is not finite. It's depending on your precision. Okay, so in the analog world, you cannot have testability proof. Yes.
So aren't we checking AX equal to B because they are double?
No. If you implement a solution of AX, right, given B to get X, then AX minus B is a very meaningful check. But if you try to use this to check this routine, it's meaningless, right? Because it's the same factor. Unless you have another way to get B. Right? I'm just showing that not all tests are good. This is a dumb example, okay? So checking the norm of AX minus B for product AX is a totally unnecessary check because it didn't check anything. Except the norm, okay? You check how your norm is implemented. Okay. Okay. So maybe I'll start just one slide, okay? One slide on the next subject that's coming, okay? I don't have that much time to deal with all the different linear algebra solution probability, okay? So I just want to claim that the most important one, if you know how to deal with this, okay, given A and B solve X, okay, in the AX equal to B, okay, you are 99% there. Okay, so there are for matrix, for the linear problem, usually you're dealing with these three problems, okay? Get a solution of AX equal to B, get X, okay, given A and B, get the X, or minimization of a residual, sorry, this is a minus sign, okay? Minus sign, AX minus B, okay? The second norm of a like a least square fit, okay? X is not exact, but you are interested to get the minimal of the second norm. The good example is least square fit, okay? It's not exact, okay? But I would like to minimize a factor, okay? Minimize a factor, and the factor is AX minus B, okay? These two you can easily prove is if you know how to solve this, you know how to solve this, okay? This is actually easy, okay? Just if the problem is linear, you take the first derivation of this guy. The minimal must be happening on the derivation in the multivariable case, right? So you are actually solving AX equal to B, okay? So it's the same, okay? It's the same problem, okay? There's a class of problem called eigenvalue problem, okay? I just want to mention the eigenvalue problem provides sufficient information for this, okay? Meaning, if I solve this, okay, if I know the eigenvalues with all the corresponding eigenvectors, then you have done everything about this matrix, okay? If the matrix eigenvalue and eigenvectors are known, then any further computation is so easy. Okay, so this is a harder problem, but you get everything in there. Okay, AX equal to B, you solve for X, is depending on how much information, okay, is in B. Okay, give you a easy example. Say B is only 1, 0, 0, right? With only 1, 1. So the B is only limited in testing that space of A. Okay? You need n kind of these B to get the full information of A. Okay? So, but if you solve the eigenvalue problems, then you have everything. Okay, so it's a harder problem. Okay, but it's just like if I need to, this is equivalent. If you know how to solve Ax equal to b, and I give if the rank is n, and I give n orthogonal b factors, and I solve all of them, then it's equivalent. I solve the eigenvalue and eigenvector problem. Okay. So it's just that these statements say 1 and 2 are equivalent. 3 contains sufficient information for 1 and 2. Okay, problem 3, if you know 3, then everything is solved. Okay. Simple proof. Okay, very simple proof will be the last slide today. Okay, so if I know all the eigenvalues and eigenvectors, okay, this is less critical. Okay, you can easily show that this matrix, okay, this eigenvector matrix have this relation. Okay, with this, and this is a diagonal matrix of your eigenvalues. Okay. Okay, so you can see the eigenvectors and the eigenvalues are many times very useful in proving all the matrix properties and things. Okay, and I'll leave that to your other class of making those proof. Okay, it's commonly used. Okay, because you know eigenvalues and the corresponding eigenvectors, you know everything about this matrix. Okay, in a solution saying that Ax equal to b. Okay, if I know these solutions, if X is the decompositions of your eigenvectors, do that very simple operations. You know that is how B can be decomposed into the eigenvectors. Then that you can find all the C1, C2, and Cn. I'm done, right? So if I know these eigenvectors and the corresponding eigenvalues, okay, then the problem of solving any Ax equal to b is to decompose b into the eigenvector composition and use this, right? I know all this lambda 1 to determine your C1, C2, and to Cn, and your solution is nothing but the combination of that. I'm really done, right? So that means a non-degenerate matrix A of rank n always have n eigenvectors that are orthogonal to each other. Okay, that also means that this is always possible, right, for non-degenerate matrix. Okay, this, I don't know how much you remember this. Okay, this is far away when you take linear algebra. One of the things that is easy proof. Okay, if your A has a non-degeneracy or meaning that the determinant is not 0, then it's always, right, can be decomposed into diagonalization or Jordan blocks, but both of them were corresponding to unique set of eigenvalues and the eigenvectors. The eigenvalues can be degenerate, meaning lambda 1 can be equal to lambda n. Okay, but the eigenvectors will always compose a orthogonal set of the n-dimensional space. Okay, for any non-degenerate matrix A. Okay, that's just a review. Okay, I don't need that. Okay, I don't need that in this class. It's just that when you this one will build you some intuitions when we do the computations. Okay, below meaning can be always be explained by this. Okay, but it's something that I don't need your computation for this. Okay, it's just that as a reminder that actually you'll be nice that your matrix with known eigenvalues and eigenvectors, you have the full solutions. Okay, and I'll focus on how to solve this. Okay, for the next 4 lectures actually. Okay, how to solve a realistic Ax equal to b. Okay, that actually contain 4 lectures. Okay, there's a conditioning, and there's a trade-off between minimal filling and pivoting. Okay, something I need to introduce to you for any practical large matrix. Solving this is not that straightforward. Okay, there are principles I need to teach you to know what contains a good solution of Ax equal to b. More importantly, how can you check how good is that solution? Okay, I'll focus on that. That was 4 lectures. Okay, and that'll be it.